Let's start by proving the linear upper bound. At a kf plus 1 iteration, we're going to be doing a weight update that takes the current weight vector of k and adds the misclassified examples vector. Now, all of these are vectors, so we can take their squares of their norms and try to use this as a proof instead. So we're going to write down this is just the first term is equal to the square of the individual terms on the right-hand side. And you'll notice here we have a square, so we're going to try to undo that square and come out with its component parts. So let's write that out. Which is the first term the last term and the middle term. And because this middle term is a negative number, right, we're adding something that is smaller than 1 because x miss was misclassified. This is a misclassified example. This is actually going to be smaller than if we just take the first two terms by themselves, right? So we can write something like this. Because again, this particular thing is smaller than 0. So when we take it out, it's actually going to force us to have a less than sign over here. So we've written this out for you. It's a little bit more clear what's going on, right? Again, here we're taking this particular component because it's misclassified as a negative value. We can take this out because it's actually subtracting a smaller value here. So now we're going to recursively apply this idea. We have the case where we have the kth iteration. We're just changing the indices a little bit and changing it to kf and the k-1 interval here. So we're going to be able to write this out and expand it out. That's for this first blue term. And we're just bringing down the second term here. And you see how this is going to progress. We can take this term here and expand it out as well. And we can just propagate the rest of the terms over. Right, so I'm bringing just this term down, and then bringing this term down, and I'm expanding this, this term out. Right? So what happens in the limit with this? We're working backwards from the kf mistake, and we're going to get eventually all the way down to and the original weight vector. Oops. And then we can take all of these extra terms that we have here and just try to sum them up. So you're just going to write it as a summation for all of the times t, all of the mistakes that we're going to make. So we're just changing indices here. Looks good so far? Okay, so we've copied out the results here, and I want you to notice something. What is this value that we're starting with? This is the original weight vector that we initialize with. And without loss of generality, we can define it to be anything we want for convenience, and we might want it to go away. So one thing we can do is set the initial weight vector to a column of zeros, right? Then the norm of the vector is 0 as well. So we can just toss that out, right? And what we're going to do with this summation over here is try to find the norm out of all of these TF iterations, okay, which has the maximum value, which has the longest length, right? Because the norm is length, so the squared norm is also some scalar value. So we're just going to take the maximum of those values and denote it as m. Okay, then it's pretty simple what we're going to come up with. In this case, where we've defined this max, right? Because we've thrown this away and we're substituting this term with a maximum. So that will be m. So we're going to get something like this. So you can see where this is heading. This is an upper bound because we're saying that the norm squared is going to always be less than some linear combination of the maximum norm that we're getting out of all of the iterations times a constant linear value, right? So for every iteration, it's going to increase by at most m. So this is a linear upper bound.